Ever wish you had a crystal ball? A way to see what's coming next? Well, in the world of data, we kind of do. Today, we're going to break down linear regression. It's a powerful tool that helps us find patterns hidden in the noise so we can make some pretty solid predictions. All right, so here's our game plan. First, we're going to talk about why we're so driven to predict things in the first place. Then, we'll get into the fun part, drawing that perfect best fit line. After that, we'll level up and see what happens when one clue isn't enough. We'll cover some common traps to avoid, and finally, we'll wrap it all up by learning how to actually read the results and make our own predictions. At its core, this is all about a really basic human instinct. We are wired to want to understand what's going on so we can figure out what happens next. It's about seeing the future, even if it's just a little bit. And that's really the whole why behind a tool like linear regression. So picture this. You've got this messy cloud of data points on a chart. It just looks like total chaos, right? How in the world do you figure out if there's a real, clear relationship between two things? How do you cut through all that noise and find a predictable pattern? Well, that is the exact problem linear regression was born to solve. To put it simply, linear regression is a prediction machine. We take something we want to predict, what we call a continuous outcome, like a person's blood sugar level, and we try to guess what it'll be by using other bits of information. You can think of them as clues. In the stats world, they're called covariates, but honestly, clues works just fine. Okay, so how does this thing actually work under the hood? Let's start with the most basic version, which is called simple linear regression. And its whole job, its entire purpose, is to draw one single perfect straight line right through our data. So if you want the more formal definition, it's a way to model the relationship between two continuous variables. You've got the outcome, the thing you're trying to predict, and you've got the one clue you're using to predict it. The whole goal is to find a single equation that best describes that connection. And the equation itself is surprisingly simple. Let's just build it together piece by piece. First up, we've got y. This is our outcome, our dependent variable. It's the thing we're trying to figure out, like that blood sugar level we keep talking about. Okay, next part of the puzzle, we bring in our clue, which we'll call x. This is our predictor, our independent variable. It's the piece of information we think is going to help us predict y. So, for example, it could be a patient's fasting blood sugar reading. And here it is, the whole shebang. Y equals beta 0 plus beta 1 times x. That is it. It's just the classic equation for a straight line. Beta 0 is the starting point, the intercept, and beta 1 is the slope. It tells us how much y changes every time x goes up by 1. Put them together, and you've got your line. But wait, how do we know it's the best line? Well, the method it uses is called least squares, and you can think of it like a competition. It tries out tons of different lines, and for each one, it measures the distance to every single data point. The winning line, our best fit line, is the one that has the smallest total distance. It's the line that best hugs the data. Okay, so that works great when you have one clue. But let's be real, life is way more complicated than that. Usually an outcome is influenced by a bunch of different things working together. So what happens when we want to use more than one clue? This is where we level up from simple to multiple regression. Instead of just one predictor variable, x, we can now throw in 2 or 3 or more. We call them x1, x2, and so on. The equation gets a little longer, but the core idea is exactly the same. We're just trying to get a richer, more accurate prediction by considering how several factors play together. And check this out. Here's a perfect real-world example. We're still predicting that HbA1c level, but now we're using 2 clues. Fasting blood sugar, or FBS, and the result of a 2-hour glucose test, MOG-T2H. The model is now smart enough to weigh the importance of both clues to make a much more accurate prediction. Now, as powerful as this tool is, it's not magic. It has rules. There are some core assumptions that your data needs to follow. If you break these rules, your predictions might be totally unreliable. So let's go over the key rules of the road. All right, so here are the ground rules. First, this whole thing only works if the relationship you're looking at is, well, linear, a straight line, not some wild curve. Second, the data point should be spread out pretty randomly and evenly around that line. And third, each data point needs to be independent. One measurement can't influence the next. Following these rules is absolutely crucial if you want a prediction you can trust. Okay, here's one of the biggest potholes to watch out for. It's a big word, multicollinearity. But the idea is simple. Imagine you're trying to get directions, and you ask 2 people,
but they just echo each other. It's not really helpful, right? That's what happens here. Your clues are telling you the same thing, and it totally confuses the model.
A classic example is trying to use both systolic and diastolic blood pressure in the same model. They're almost always highly correlated. The source material points out a correlation of nearly zero point 0.7 in one case. Because they move up and down together, the model has a really tough time figuring out which one is actually driving the effect. All right, now for the payoff. We've built the model, we've checked the rules. So how do we actually read the results? How do we turn all these numbers into something meaningful we can actually use? Let's go back to our simple model from Table 1 of the source. Remember, we're predicting HbA1c using just fasting blood sugar, or FBS. Now, the two numbers we really care about here are sitting in that estimate column. So the real skill is translating those numbers into a plain English sentence. That estimate for FBS, the 0.3784, that's our slope. And here's what it tells us. For every single 1 unit increase in a person's fasting blood sugar, our model predicts their HbA1c will go up by about 0.378 units. We've actually put a number on the relationship. And this is how you actually use it. It's basically a recipe. You take the estimates from the table and write out your equation. The intercept is your starting point. Then you add the slope multiplied by the fasting blood sugar. So you just plug in a value, let's say a fasting blood sugar of 5.0, do the quick math, and boom, you've got your prediction for HbA1c. So you see, whether it's in healthcare, finance, or climate science, linear regression helps us find the signal in the noise. It turns a mess of data into a clear story about relationships, and that story lets us make educated guesses about what's coming next. So the real question isn't about the math. It's about what you will do once you can see the pattern.